it's María Luisa Bonet.
Yeah.
Hi, well, thanks for inviting me to this, Antonina, and well, the first thing is, as you see in the title, there's, I'll probably keep on changing between automatability and automatizability. And I think, the automatizability title that nobody likes, right? I think it's my fault, right? Because in Spanish, you wouldn't say automatability. So I don't know. You will see a variety of titles here, and the first thing I want to show are some fakes, So, so this is Toni and I, in San Diego, which is where we met, right? This is like a collage. I didn't make it, that was my son, who was working on this, pulling pictures, and the math department in the back. I don't know if you remember the building, right? So we met when we were both a postdoc at UCSD, right? So Sam first told me about you, Toni, that, somebody who had solved this really important problem, the lower bound and so on, was coming, to work with, Russell. So eventually we met, I don't remember the exact moment, and we started working together, and what's most important for me, this is another fake, the friendship that developed, that was much more important for me, to be honest with you. And so we would work together at the math department, the building you saw before. And then around 5, we would go to the beach, we couldn't figure out the exact spot, right? And ran, and chatted, all the way through, right? So, that was, those years were probably some of the best of my life, and the friendship was, for me, even though, the work was great, and I love collaborating with Toni, like all of you, our conversations and activities were, for me, the most important, really. So I'm going to talk about something old, because, well, it's something that I think people are still interested in, right? Which is the weak automatizability. People have really outstanding results on non-automatizability, and there are some open questions, and I want to remind you guys what happened a long time ago with Toni, basically, and Ran, the three of us, and, have a discussion. I talked to some people, you will see in the slides, Anyways, so let me remind you that a propositional proof system is something very abstract in Cook's definition. Actually, the reference is not there, but everybody knows, it's something very abstract. It's just a polynomial polynomial time computable function from strings to the set of all tautologies, right? And you can see it also as a verification procedure, that you have a pair, possible proof, and formula, and if this pair is accepted, that's a proof, right? And you have to have, accepted instances for all the tautologies, basically, right? And the fact that this definition is so abstract has a lot to do with the weak automatizability, the way I see it, So anyways, the first question that, was, posed by Cook and so on was, how big are the sizes of these tautologies or the refutations, right? But at some point we were very interested in, okay, we know that there will be tautologies or contradictions that will require very long proofs, right? But if the proofs of refutations are small, could we have procedures to find them in a reasonable time, right? So this is how this research started between the three of us, right? So we invented this term, right? And this definition, right? So you have a proof system and you want to know if it's automatizable in the sense of, is there an algorithm? What? No. I will.
There are different versions on the same slide.
Yeah, that's why the title was Automat with a start. Actually, Antonina came up with this title. I was looking for ideas, and that's her contribution, which is a very good one. And I keep on saying automatizable and automat. I cannot say it.
I actually almost emailed the staff saying, "Oh, she probably put the star in there as an accident. You might want to take that out."
No. No. Okay. Anyway, so a proof system would be automatable. I don't even know how to say it. If there exists an algorithm.
Yeah.
What?
Hot.
If there exists an algorithm such as, it takes a formula and returns a proof P in that system, okay, that's automatizable in that system in polynomial time in the size of the shortest P proof of that formula. So that was our first definition. But there are other, variants, like quasi-polynomial time automatizable, like this property tree-like resolution has, and this has been discussed previously. And also we have the notion of weak automatable. Okay. And what does this mean? So it means, okay, and it makes a lot of sense, in a lot of practical sense, you don't want to force, the procedure to output a P proof, right? But maybe some other proof, right? So here I have a definition of weakly automatable. And and I will show you several equivalences. So P is weakly automatable if there is an, well, I cannot say it, I'm sorry. P is weakly automatizable if there is an automatizable proof system that simulates P, okay? And here are some, equivalences. But before I show you, and we talk about the equivalences, there is like a notion that helps understand what's going on, and it's related to this abstractness of the definition of what a proof system is. Okay, so there's this notion of disjoint NP pair. So this joint NP pair is something very simple. You have two problems in NP, and that their intersection is empty. Okay. It could be, for instance, graphs that are a color, the colorability and the yeah, click. I couldn't say that. Yeah, click and coloring, right? So I think that it was Rasparov that came up with the idea of talking about canonical NP pairs for a propositional proof system. So what is that? So a pair, so this is a pair, right? And ref of P is you have a formula and, and a size, okay? And so that P has a reputation of that formula in size M. And the other element in the pair is SAT. So you have the formula and the size, and the formula is satisfiable. Okay, so what do we know that is equivalent? And I think Putlock proved some of this. Albert and I, in another paper, several people have been noticing these things. The canonical NP pairs for a propositional proof system being polynomially separable is equivalent to various notions of weak automatizability, like the one that I was telling you before. Like there is another proof system that simulates P and that is automatizable, or another notion that is that there exists an algorithm that for a proof system that returns proofs, in in the size of the shortest formula, they don't need to be, yes?
Comment from Jan Johansson. In 2000, it was automatizable. Then in 2020, it's automatable. 2030, it should be automable. And 2040, it should be autable.
Well, I think I can only say one of this. Yeah. Okay. So, and this equivalences, the reason for all of this is that a proof system is something, it's a, polynomial time procedure, basically, for checking whether something is a proof of a tautology or not, right? So, well, here I have interpolation with Krajcek's name, but I mean interpolation, Craig's interpolation interpreted by Jan Krajcek, right? So this is an observation. So you have F and G that have, it's an unsatisfiable conjunction. And given an assignment for the common you have X variables that are common, Y and Z that are not common. So if you give an assignment for the X variables, then either F or G is unsatisfiable, right? So, that gave rise to the interpolation problem. You have an unsatisfiable formula, okay? And given an assignment alpha to the X variables, you want to know which part is unsatisfiable, F on G. And the problem is, well, return 0 if it's F, return 1 if it's G, okay? So then we can talk about a proof system having the interpolation, a feasible interpolation, right? If the interpolation problem is solvable in polynomial time respect to the smallest P refutation of this conjunction. Okay. So, well, that was the first paper that we wrote. I mean, I think we used this observation. I think this observation comes from Russell, and it's in our paper, saying that if P is automatizable, or actually in this case, weakly automatizable also, then P has feasible interpolation, right? And it's a very simple idea, So you suppose that P is automatizable, right? So if n is the size of the smallest P refutation, and alpha is an assignment of the common variables, you use the automatization procedure on F with alpha and run it for polynomial number of steps. If you get a 0, I mean, then you succeed if you get a 0, because that means that F is unsatisfiable. Otherwise, you write a 1. There's a property that you have to have here about refutations, which is if you say, for instance, G is satisfiable if you put, if you assign values to the Z's, the refutation of F should come from the refutation, should be embedded in the refutation of the full formula. And I don't know the name of this property. I mean, I don't remember.
Closed under restrictions.
What?
Just as closed.
Closed under restrictions? Yeah, something like that. Okay, so this is how we started, But, this all comes from a paper by Krajcek and Putlak, because they were working on non-feasible interpolation for extended Frege, right? But, we, reduced the complexity of the proof system and made the connection with the automatizability. Okay, so this is, everybody knows what the Frege system, I mean, we've heard a lot about, this is just a textbook definition with the modus ponens, some axioms, bounded the Frege, AC0 Frege, you have a constant number of alternations of n's and or's. You can put the negations at the bottom level, and the connectives have unbounded degree. PC0 Frege, it's unbounded de Frege. You have threshold and parity connectives and rules for them, okay? So actually, what did we use? So actually, let me go forward a little bit. So we want to show that Frege systems and even TZ0 Frege systems don't have feasible interpolation under some cryptographic assumptions. So this is the cryptographic assumption we were working with. And I've been trying to remember all the places where we've had discussions. And I think we were in Israel, and I'm not completely sure, talking to Moni Naor. Is it possible, or I'm making it up? And he told us about Diffie-Hellman. I remember going into his office, and I think it was in Israel. Anyways, what is Diffie-Hellman, right? So you have Alice and Bob. They both have, they don't share. I mean, they have a secret, a large secret. Okay, so we're going to do this first of all using the multiplicative group ZP, and we have a public generator G. Okay, and Alice has secret A. I don't know how to point to this,
Red.
Huh?
Red button.
Red button, I don't see a red button. Ah, yeah, okay. And Bob has a large secret B. Okay, so what is it that they do? Alice sends G to the A mod P, okay, to Bob. This is public, and Bob sends G to the B mod P to Alice, okay, and now they both compute G to the AB mod P, each one of them, right? So they share some information that nobody should know, okay, unless this procedure is just not secure, right? So if you do it with a product of two large primes, then breaking Diffie-Hellman, is harder than factoring. Anyways, so this is what we were going to use, right? So it took it took constructing this conjunction A0. Here is one part, A1 in the form of the feasible interpolation, right? So we have variables X and Y that are common, X and Y that are common in both formulas, and non-common variables AB and CB. Okay, so what is this formula saying? This formula is saying that X is the same as G to the A mod M. Okay, Y is G to the B mod M. Okay, and the last bit of G to the A mod M is 0. And the other one will say X says G to the C mod M is X, G to the D mod M is Y, and the last bit of G to the DC mod M is 1, right? Why is this a contradiction? This is a contradiction. Okay, so A0 and A1 is unsatisfiable since, okay, since we know that G to the A is X, okay, everything is mod M now, let's just, okay. So, but they also tell us that G to the C mod M is X. So now we put G to the C. We commute these two because this is a product. And then G to the B is Y. And also G to the D is Y. So we get this. So A to the AB equals G to the DC mod M. Right? So since these two are equal, it's not possible that the last bit or whatever is 1 and 0. Okay. So this was a lot of work because we had to encode all this arithmetic, improve all kinds of properties, etc., etc. Right? And well, we got the non-feasible interpolation under this cryptographic assumption. Also, no system that simulates them has the feasible interpolation. So these systems are not automatizable or weakly automatizable. And then we wanted to get lower proof systems, and we got a weaker result for AC0 Frege. Okay, so if we go back to this, so Frege doesn't have feasible interpolation until unless factoring is solvable in polynomial time, and for this one, unless factoring can be computed in sub-exponential time. So the result is weaker because basically what we do is like, is like we work with polylog fanning thresholds and connectives in TC0 and simulate that in AC0 Frege. So we do some kind of weak simulation of all the work that we've done with the TC0 Frege. Okay, so that is a lot of proving, all these properties, and eventually we get that AC0 Frege is not automatizable or weakly automatizable under, this not a strong conjecture, right? So, this is the state of the situation at this point, as far as I know, right? So if we think about non-automatizable systems, under assumptions, well, there's this, great results that have appeared lately, about resolution, ResK, null-Stalin sets, and polynomial calculus, cutting planes. Shirley Adams, I've heard that some people have solved this, Oh, okay, so it's not clear. Okay, I have a question mark because I wasn't sure, So is this fine? Okay, fine. And as far as I know, it's open for sum of squares, really open. Okay. And okay, it's not true that there are no more results on weak automatizability. I will show you more, but it's not clear that the assumptions are strong. We will see it now, okay? But so far, this is what was done in the 90s, right? Okay, so I wanted to have a little discussion of what else do I know about this? And, this is through conversations with Albert and Pavel, okay, so there are 3 papers, and Toni is involved in one of them, again, that relate. Okay, so basically, the idea is to look for problems that you think that are in NP intersection co-NP and not likely to be in P, right? Like what we did with the factoring and the cryptography. And so there's this graph games, okay, several of them, right? And we know that deciding whether a player has a winning strategy is in NP intersection co-NP. And so what people did is show that, for instance, if depth D Frege, or very low depth Frege, is weakly automatizable, then these games can be decided in polynomial time, right? So if people expect that they will not be decidable in polynomial time, you wouldn't expect this low depth Frege to be weakly automatizable. It is not clear what will come out of this because there are quasi-polynomial time algorithms for solving parity games, right? So I don't know. I don't know.
There's still nothing for simple stochastic.
Huh?
Up or down for simple stochastic game?
Well, I don't know. I mean, I got this through Pavel, actually. He's the one who found this paper, and others that have improved on this, and they have quasi-polynomial time algorithms for parity games. And I've looked through, I've done a search, and I couldn't find quasi-polynomial time or polynomial time solutions, for deciding winning strategies for the other games, right? So I haven't found that, but yeah.
Aren't the other games special cases of parity games?
Oh,
it's the other way around. Okay.
right.
Sorry.
So I wanted to mention this, also because it's, Tony's work too. Yeah.
It's just fair to say that this quasi-polynomial time algorithm arrived after those
Yeah.
papers.
I don't
So some
know,
of those
yeah.
Papers were done with
Actually, I suppose,
2017 for the collude. The last paper is from 2017, so it's pretty recent.
yeah, actually, yeah.
At that time,
It was the
I
best
should
paper.
have-
It was the best paper in stock. In
Yeah, I
2017.
At the
should
time,
have-
we didn't know that these were. like,
Yeah.
Right. No, I should have said that, and I looked at the dates and everything, but I have forgot. I mean, I forgot. Okay, but I wanted to mention this because they're very interesting results, but we don't know, whether they will take us somewhere or not, right? So this is some silly dead end, right? Okay, so people have talked about automatizability here, and they have mentioned, such and such proof is automatizable because they were thinking in terms of if some algebraic proof system has an algorithm, that can find refutations of the, using the degree rather than the size, right? So here we're working with the size, right? And so for instance, can we use any of the, so this is a silly no, okay, but I'm just gonna mention it anyways. So for instance, for resolution, I mean, could any of these procedures, for Shirley-Adams, sum of squares, or polynomial calculus automatize resolution in the sense of the size? The answer is no. Why not? It all goes back to that tautology. I don't know if I or yeah. So the order in principle, right? So we have a contradiction, right? That has that requires high width, like square root of the number of the size, right? But it has small refutations in resolution. So the natural question is, what happens when you look at this contradiction in, for instance, polynomial calculus, whatever, right? So people have looked at that, like Nicola, Massimo, and Potenchin, and they've seen that this ordering principle also requires pretty high degree for various other algebraic systems. So we know those procedures are not gonna automatize resolution. I mean, I wanted just to mention this observation, basically, right? What else? Well, there's this system, right, which is ResK. What do we have? It's like resolution, but we can have inside our clauses, we can have conjunctions, of up to k literals, right? So this is a clause, a ResK clause, where your conjunctions are at most of size k. And these are the rules of inference. You can do weakening, you can do introduction of the conjunction, right? So you have A or L, B or this conjunction, and if S is less or equal less than K, then you can conclude this, okay? And you can do some form of cut. Well, actually it's a cut. And you have A or this conjunction, and then you have B or not each one of this, then you can derive A or B. Okay, that's the system. And we worked on this, with Albert long time ago, right? And we used this reflection principle, which is different. I mean, again, the reflection principle has been discussed here in a very different sense than what we used it for, right? I don't know. I mean, I think Pavel and Jan were the first ones to define this reflection principle, right? And it says, okay, so you have the form of the interpolation in this formula. You have XC and XY variables, and SAT and M means that X encodes a formula of n variables and m clauses, and Z encodes a satisfying assignment. And on the other side, the ref says that Y encodes a refutation of X of size S, and you have N and M for number of variables and number of clauses, okay? So clearly this formula is unsatisfiable. And Putlock has this theorem that if the reflection principle has polynomial side reputations, the polynomial, okay, so if the reflection principle has polynomial side reputations in a proof system that has feasible interpolation, okay, just a second, I'm saying it wrong. The reflection principle of some proof system, okay, has a polynomial side refutation in a system that has feasible interpolation, then this proof system is weakly automatizable. And the reason is just that you can separate the NP pair, the canonical NP pair for that proof system, basically, right? So that was interesting for us, right? So one of the things that we did is that we proved that Res2 proves the reflection principle of resolution, right? So we had these equivalences, not all of them, most of them, and maybe none of them require that K is a constant, but basically we know that resolution is weakly automatizable if Res2, for instance, has feasible interpolation, right? Because, okay, we have Putlock's theorem that if you have the reflection principle full resolution has polynomial side refutation in a system that has feasible interpolation, then you can weakly automatize resolution, right? So it would be interesting to know, and many people think that this is not going to be true, whether Res2, for instance, has feasible interpolation, right? And, even Putlock thinks that this is not going to be true. Okay, so, well, what do we know about feasible interpolation in Res2? Esteban, Galesi, and Messner showed that tree-like Res2 has monotone feasible interpolation, but Res2 non-tree-like doesn't have monotone feasible interpolation. Okay. So, and then, okay, so let me go back just a second to Putlock's theorem. Okay, so to figure out, say, for instance, to conclude, that resolution would be weakly automatizable, which many people think that that would not be true, you would need a system that would prove the reflection principle and would have feasible interpolation and some other conditions like the closure under, how did you say it, Toni? Closure and restrictions, right? Okay, so Res2, it would be interesting to know if Res2 has the feasible interpolation property because it proves the reflection principle. But the thing is, okay, well, we know many proof systems that have feasible interpolation or monotone feasible interpolation. Could they prove the reflection principle of resolution, for instance? Okay, so this is what I wanted to, discuss a little bit here. Well, cutting planes has monotone feasible interpolation, but requires exponential size refutations of the reflection principle, okay? And this is a result by Pavel again. But these other systems, like Shirley-Adams has monotone feasible interpolation, polynomial calculus also, sum of squares seems to have feasible interpolation too, Loba-Schreiber, etc. But we don't know anything as far as I know about whether they can prove, say, the reflection principle for resolution, right? Well, it's an open question. Anyways, so now, oops, these are not fakes, right? So, I'm really happy, I was into this technical thing and I forgot, that we were celebrating you know, so we're back to working together, back to having fun together, chatting, conversations, you know. And I'm really happy to be celebrating, you know, your birthday and above all your friendship, you know, and you know, which is so important for me, you know. And I hope we continue, you know, and you know, and we can have more pictures, not fakes, right? Of us, you know, working and having fun together, conversation, sharing our lives, etc.
We're running a bit behind schedule, so I guess we'll take questions to the break. And let's say we reconvene at 11:50, so in 20 minutes.